Lesson 11:10. Single slit diffraction, limits of resolution and thin film interference. Alright, turns out that waves bend around barriers. In the first picture, these are both water waves, but they behave like any other wave. The waves hit and you can see the end of little walls, and you can see that there's a little bit of bend here. But that's when the opening is large compared to the wavelength. If we narrow the opening compared to the wavelength, it bends a lot more. Large opening is small bend, small opening you get a large bend. This is diffraction. It's the bending of the light. You would think that when you shine light through a little opening, it's just going to go straight through. You're going to get a dark spot, like down here on this first picture. But in reality, when you shine light through a little opening, it spreads out. Like this picture. That's what's really happened, not that one. Single slit will produce a diffraction pattern. The Huygens wavelets interfere with each other. And our previous two interference things, it was two openings or mini openings. So you had these separate rays or waves of light that would interfere with each other. In single slit diffraction, a single beam of light interferes with itself. So you think of each little photon, each little tiny piece of light as being a Huygens wavelet that interferes with other little wavelets. The center band will be bright and is twice the width of the other band. So here's the geometry. The first order dark band occurs when the left edge and the right edge paths differ by 1 wavelength. Ooh, why? I thought that that would be bright. So, if you look over here on the right, here's the light from the first little wavelet, and here's the light from the next little wavelet down that's half of a wavelength different. These two cancel out. And then, use a different color, the wave from 2 and 4, they're going to differ by half a wavelength. They cancel out. And the wave from here and here, they'll cancel out. So eventually, every little bit would cancel out with every little bit. And yes, there's this tiny, tiny little piece here that doesn't cancel, but it's so tiny it's not noticeable. Everything else canceled out. The center wave path length differs by half a wavelength, leading to the destructive interference. The wavelet slightly below number 1 cancels with the wavelet slightly below number 3, and you just keep going all the way down, and it all cancels out. All right, so if we take this, and that angle is theta. That's a right angle. So our sine of our angle is opposite, which is our wavelength, over hypotenuse, which is W. For multiple dark fringes, we're going to multiply by m for whatever dark fringe we are. So theta is the angle between the wave and the normal to the slit. M is the dark band order. Lambda is the wavelength, and capital W is the width of the slit. Now, for multiple slit diffraction, this was bright. Now it is dark. The single M. Single slit is different. A laser shines through a single slit width of 3.25 times 10 to the negative 6. That'd be 3.25 micrometers. The first order dark fringe is 10.2 centimeters from the center, and the slit is 50 centimeters from the screen. What is the wavelength of the laser? So draw a little triangle. Again, I have my laser down there, and my screen is up here. So this is the first order dark fringe, so that's dark, and it'll be m equals 1 because it is first order. Distance to the screen is 50 centimeters. Hey, look at that. We can use tangent to find our little angle theta, which is about 11.53 degrees. Now we can use our single slit diffraction formula to find the wavelength of the laser. All right, I know the width of the slit there, and I know m is 1, and I know my angle, so I'll just plug it all in. Multiply by the 3.25 times 10 to the negative 6, and you get your wavelength as 6.50 times 10 to the negative 7, or approximately 650 nanometers, which is the wavelength of a red laser. Some applications. Think of making microchips. They're very small electrical components are used. In fact, what happens is we make a mask like a photographic slide. So you have this thing and you draw where you want all your little circuits to go. And light shines through that onto the silicon wafer, and it's coated in a photosensitive material. So you've got your wafer here, and you've got your mask here, and the mask has these lines and things on it, and you've got a light bulb shining light on it. And so it shines through onto the silicon wafer below it. The exposed portions are removed later. However, if too much diffraction occurs, think of diffraction occurring, and so these are nice and wide. What's going to happen? Oh, well, they could overlap each other, and then your microchip's useless. Currently, they use ultraviolet rays, which have smaller wavelengths than visible light, to minimize the wavelength to width ratio. So eventually they're going to move up and start using X-rays and maybe gamma rays. Of course, those are dangerous, so, you know. Light going through a circular aperture also has diffraction. It's also true for light from lenses and mirrors. But the first minimum will occur at that. So that's the first dark spot. So you actually see a bright spot, and then a dark ring, and then a bright ring, and a dark ring, and a bright ring, and a dark ring, like such. First minimum is there. Multiply by m if you want others. Your angle is in radians because we're doing an approximation. Your angle is in radians. Wavelength, and d is the diameter. Ooh, we usually use radius. This one uses diameter. Two light sources are called resolved when one center is at the first minimum of the other. So think of driving down the road and you see a car a long way off. And when you see the car a long way off, you just see one set of lights. But it looks like a single light. As it gets closer, you see that it's stretched out. And then when it gets really close, you can see that it's two separate lights. This one here is the resolved one, the one that's just resolved. So you have your minimum, there's the center. So that one's resolved. What is the minimum angular spread of a 633 nanometer wavelength helium neon laser beam that is originally 1 millimeter in diameter? Okay, well that should be pretty straightforward. Just use this little formula. What do we have? Well, this is our wavelength. Use a color we can see. That's the wavelength. And then that is the diameter there. Make sure you convert them both to meters. And so we get about 7.72 times 10 to the negative 4 radians. That's awfully small. All right, but then we're going to shine this at a mountain cliff 15 kilometers away. How big will the illuminated spot be? Well, we can use tangent here. On this little triangle, and this distance is x, and then we have y. Tangent's opposite of adjacent. Opposite is y, adjacent is x. That it would be 15 kilometers away for x, and we're looking for y. At the moment, plug in our angle. Make sure your calculator's in radian mode. Hit mode, change it to radians, then make sure you change it back to degrees when you're using degrees. 15 kilometers is 15,000 meters. Multiply by that, and you get y is about 11.58 meters. So over 15 kilometers, one edge of the light spreads out to 11.5 meters. So this is 11.5. And this is 11.5. And so our total width of our bright spot is going to be 2 of the y's plus the original width. It'll be y, let's use a different color, it'll be y plus the spot in the middle. All right, so it'll be 2 times 11.58 meters plus the original spot, which was 1 millimeter. Which means our bright laser spot will be 23.2 meters across. Think of that if you are military and you're using a laser guided bomb, you're shining your laser to the opposite side of the valley, several kilometers away. That spot that the bomb's looking for is going to be awfully large. Light interference depends on the ratio of the wavelength to the object's size. If the object is near the size of the wavelength, there will be interference. Since each color light is a different wavelength, that light can be split using thin films. When light reflects from a medium having an index of refraction greater than that of the medium in which it's traveling, a 180-degree phase change occurs. So in other words, your light's coming in like such, and it hits something. Hits something right there. When it reflects back, if the index of refraction is more, let's say this is 1 and this is 1.3, it will flip over. So it was coming in like that, and now it's going to flip over. Reflect back that way and transmit this way. That's what I mean by 180-degree phase changes. Exactly opposite. So here's how a thin film works. Light comes in and hits this first boundary. Is it phase shifted? Well, it is if N2 is greater than N1. The transmitted light, so now we're down here, hits the second surface. That one down there. If it's phase shifted, if N3 is greater than N2. and then it bounces up. You'll have destructive interference when the distance, we're thinking this is really small, remember, super thin, that this down and up is approximately 2t. So if this distance is whole number of, or sorry, half of a wavelength, that's why we have lambda over 2, if it's half of a wavelength difference, then you'll get destructive interference. They both phase shift. Or if we don't divide by 2, if only one phase shift, because one would already be upside down. So if I wanted destructive interference, then I'd have to have one of the rays actually go half a wavelength further so that they meet correctly. And our wavelength in the material is the wavelength divided by the index of refraction. Constructive interference will be the exact opposite. So we want it to arrange so that crest makes crest, destructive interference when trough meets crest. All right, let's see how this works. An oil slick on water is 120 nanometers thick. So see, we're talking thin here. And illuminated by white light incident perpendicular to its surface. What color does the oil appear, given that it has an index of refraction of 1.4? All right, so here's what we have. We have our air on top, and then our oil, and then water below that. The oil is floating on the water. All right, ray 1, phase shifts. Why? Because we're going from small index to big index. That means it phase shifts. Ray 2, the one down here, does not, because we're going from big to small. It will phase shift when going from small to big N. Ray 2 is going big to small, so it does not phase shift. All right, we want constructive interference, so we want a difference of one wavelength. So that means our thickness, our distance that the light travels, it goes 1t, 2t's, we want that to equal our wavelength, half of our wavelength. Why? Because one of them has already shifted sideways, so if we didn't have any difference of wavelength, they would have destructive interference. We want constructive interference, so we need this distance to be half of a wavelength. All right, and our wavelength is our wavelength in a vacuum divided by the index of refraction. So I'm just going to substitute that in. Took this and plugged it into there. All right, fill in our numbers. Our thickness, our T, is the 120 nanometers right here. That's T. And our N is the index of refraction, so that's our N. Multiply, and you get 672 nanometers. Well, what color is that? That is red. If you look at oil slicks in the parking lot, you'll often see rainbows, but very often the biggest color is red. Or so they tell me. Remember, I'm somewhat colorblind. I don't really know. Have a good day.